Hello and welcome again to the lecture course on quantum gravity. Before I discuss chapter 2.2 on the covariant approach, let me add here some remarks on possible quantum gravity effects. So, of course, quantum gravity should also be a physical theory, so there should be experimental tests. And what about atomic physics? We have seen the graviton is a particle of spin 2, and so if you have an excited state, then we expect also there is a transition to, say, the ground state by emission of a graviton. Of course, the standard transitions are by photons. This is what you all have learned. So what would be the strength of the gravitational transition? Well, if we have the decay rate gamma g and compare it with the electromagnetic one, what would we expect? This is an expectation. I mean, this is the fine structure constant of electrodynamics, so we would expect some power here. And the electron mass determines the gamma E, and the Planck mass sets the scale of gamma G. So somehow we would expect. But how do we do the calculation? We use the linearized theory developed in 2.1. And so if we address the hydrogen atom, so we have as initial state, say, the excited state, 3D, and the final state, the ground state, 1s. So I need at least 3D because this has spin 2, and so I need, say, L equals 2 as the initial state to go to L equals 0. Now, already Bronstein in 1936 made a suggestion how to get gamma G, although he did not do that calculation. So he said, okay, this is by P over H bar omega, and P is the emitted radiation of classical gravitational waves. So you just take the classical formula, which was known at that time, I mean Einstein's formula, and divide by H bar omega, which is the energy of a graviton. So this is the emitted radiation for classical gravitational waves. And so in the quadrupole approximation, okay, we would have the following. So gamma G from the initial state to the final state would then be 2. So this is from the relativity 1 class, 2G omega to the 5 over 5 H bar C to the 6, and so we have the sum over K and L. Now you have these terms with the quadrupole tensor here from I to F, and Q KL from I to F minus 1/3 absolute value on the sum over all K, Q KK from I to F squared. I should say, compared to relativity 1, there's another convention here for the quadrupole tensor. It's not chosen traceless. The reason is that I want to be in accordance with the literature here on that, so you should not be confused. But anyway, this is a small issue. So here QKL is here defined as, if you take the speed of light, also here the integral d3x xk times xl times t 0 0. So not with, so without the trace term. And so in quantum mechanics, then you would translate this into a, I mean, heuristically into a matrix element, me integral d3x psi f star of x xk xl psi e of x. Now these are the wave functions that correspond to the retrospective states, and these of course are the wave functions you know from quantum mechanics 1 when you solve the hydrogen atom. So now you have to do the calculation, and this is straightforward but lengthy. So what do you insert here? So we have here, the final state is psi 1 0, 0. I mean, if we have here NLM in the standard notation, and this here would then be psi 3 to m, yeah, and m is to be summed over from -2 to +2, magnetic quantum number. So that's what you would have to insert, and then of course you have to do these calculations, and then okay, calculations, and okay, you can try yourself to do that, and what you find is gamma g is a g me cube c times alpha to the 6 over 360 h bar squared. No? So you get a nice expression, and so yeah, a nice expression here, and you see here the power of alpha is alpha to the 6. Yeah, you have also, I mean, you have here the third power of that, so maybe here we don't have this correctly estimated, but anyway, this is what you find from the calculation, and if you insert a number, then you get 5.7 times 10 to the minus 41 over second, which corresponds to a time which is the inverse of the decay rate of gamma g to the minus 1, which is of the roughly 5.6 times 10 to the 31 years. Yeah. Okay, so this is a very long lifetime of that, and so if you prepare this initial state and you want to make the experiment, you have to wait very long. Of course, you can take many atoms, and in fact, in principle, this is possible because maybe some of you who know about particle physics remember there are generalized theories such as SU5, and these theories predict a finite lifetime for the proton. So the proton actually decays, is not stable in those theories, and it's of the order of the same order, 10 to the 32 years. So in principle, you can test this, and people in particle physics, I mean, they had created huge water tanks to test the stability of the proton, and actually found that the lifetime is much longer than 10 to the 32 years. So why not doing a similar experiments here? Well, that's not so simple, because here we have, of course, the electromagnetic transition, and this will totally blow out all effects. So if the only transition were the gravitational one, maybe one had a chance, but not like that. But it seems that by going to, say, atomic and molecular physics, there could be some place where maybe the electromagnetic transition is very small, and therefore you could see such an effect. But no precise calculations and predictions are yet available. Okay, so this was a small appendix on the first part, actually on the when we developed the linearized theory of quantum gravity. Let me now go to the second part, which is actually path integral quantization. Yeah, so the covariant approach, if you these days see the literature, it's mainly about path integrals. Yeah. So it's not about just saying having as originally S matrix calculations directly in direct perturbation, say, but use the path integral quantization from where you also can then develop perturbation theory. Now in quantum mechanics, if you recall, we have for the same formalism, different so-called pictures. You can have with wave functions that depend of time, or with operators that depend of time, or you can use the path integrals there too. So in quantum mechanics, so we have the option of having the Schrödinger picture, which is maybe the most prominent one and also maybe the most far-reaching one, because it can give you directly entanglement and the like. Then, of course, you can sometimes use with probably the Heisenberg picture, or you use path integrals, some people, because path integrals were mainly developed by Feynman. You can have the Feynman picture. No? So these are the path integrals. And if you not already know about this, I recommend to read some text. Of course, there's still the old text by Feynman and Hibbs. Very nice, although there are many modern books. Feynman and Hibbs, not Higgs, no, Hibbs, of 1965. So a nice textbook in the Feynman style. Yeah, what a quantum mechanical path integral is, I mean, you write down an expression for a propagator for a particle, I mean, which is a quantum system to go from an initial position x prime to a time t prime to another position, say x double prime at time t double prime. So we like to write this down in this form. So this is this propagator. And that this can be written as a sum over all paths from x prime to x double prime, and I write this as dx of t e to the I, imaginary unit, and the action of the system that depends, of course, on all these paths, divided by h bar. No? So you see here the h bar is very relevant because you measure the classical action, which has dimension of an action, and by, I mean, the quantum of action, which is the smallest action that you have. And so you see this is very natural because the h bar is something very natural. Of course, this is a formal expression for a certain limiting procedure. Formal expression for a limiting procedure. And yeah, I don't write this down. I mean, you discretize and you make some limits. And some of you, I'm sure, have learned about it. Others are invited maybe to look into it a bit in the literature. Because you should not, or you must not think that this is something as simple as an ordinary integration. There is really some mathematics behind that and to define that. Now, this has also advantages and disadvantages. I think if you are interested in calculating, say, the spectrum of atoms, such as the hydrogen atom, which you do with the Schrödinger equation, you can do it here, but this is very complicated. Actually, only in 1979 was it possible to do it in the with path integrals. So that's not convenient, but other things are convenient to do, and one thing is the semi-classical approximation, which is an expansion in powers of h bar, and it's very natural because the h bar is here in the exponent, and also perturbation theory. And you expand here this, and okay, this is typically has a kinetic term and potential terms, and the potential terms also connect interaction terms, and so you can make an expansion in this interaction and use and derive perturbations here. And Feynman very nicely has developed a diagrammatic language for that, the so-called Feynman diagrams, that you can, I mean, straightforwardly then derive from expanding the path integral. So, I mean, of course, these pictures are not independent, and already Feynman has showed that here, I mean, for t, I mean, this is t double prime is t prime bigger than 0, that this here obeys the Schrödinger equation. And yeah, so we call this a propagator or green function, and this obeys the so-called composition law. That, I mean, to arrive, I mean, at the initial, to arrive from the initial to the final state, you can first go to a intermediate state before you go from the intermediate to the final, and then you sum over all the intermediate states. So composition law fulfilled. This will not be the case for quantum gravity because of lack of external time. Now, of course, in quantum mechanics it has nice applications, but the main purpose for introducing the path integral was quantum field theory. And there it really shows its full power. And so this is quantum mechanics. Okay, in quantum field theory, okay, you write down then, you have, okay, fields, so say a scalar field, which stands now symbolically for all fields. You can have additional indices, and x is space-time point. You can have integral over d phi of x, then e to the is, and you have all field configuration. Now, particle physicists often use h bar equals 1, but the h bar is always there, you should not forget. Now, and okay, you can give this a name. For example, you often find here z of phi. I mean, this is just a name for that path integral, for that propagator, because also in statistical physics it's used, and there it's a partition sum. Or you write something like in, out. Yeah, so these are the names given for that, but it's always a propagator, as in quantum mechanics. And in quantum field theory, you often use the so-called Euclidean formalism. Yeah, the point is that, I mean, here with the I, so this is oscillatory and very difficult actually to define mathematically. It's possible to some extent, perhaps you know these Fresnel integrals from optics, but nevertheless it would be much better if you had here some e to the minus s, with s something positive. Anyway, this here is also very complicated and cannot even be defined in a mathematically rigorous way in the sense of Lebesgue measure. Okay, so if you're at that level of rigor, say having Lebesgue measures, then maybe you will not like path integrals. But particle physicists are pragmatic, so if they think the formalism works, then they adopt it. So just to be careful. Now, so often, then we have the Euclidean formalism. Which also gives the partition sum in statistical mechanics. No? Also relevant for statistical mechanics. And so what you do is you make a formal rotation of the Minkowski time variable t to minus I tau. So you use a complex time instead of the real time, and if you do that, and this is called a Wick rotation, in the complex plane, then the action transforms as follows. So if you have ei s of phi, then you have ei, and let us write down the action dt d3x, and say for a scalar field you have 1/2 d phi over dt squared minus 1/2 nabla phi squared. Yeah, this is in Minkowski space-time, minus v of phi, and then you have this interaction term. And if you make that Wick rotation, then I mean as t goes to minus I tau, then you have to do these substitutions here, and you find minus integral dt d3x 1/2 d phi over d tau squared plus 1/2 nabla phi squared plus v of phi minus L interaction, which we call then minus the Euclidean action of phi. No? And the advantage is that this Euclidean action is bounded from below and has improved convergent properties. I mean, just if in the usual integrals, if you have e to the minus x squared instead of e to the I x squared. Okay, so this is quantum field theory, and this has widespread applications. Also, there are rigorous theorems behind that, so that if you do calculations here, you can make an analytic conjugation back to the Lorentzian, and you get the correct propagators there. That's usually guaranteed. In quantum gravity, things are different and more complicated. So, I mean, the first one who has applied bound integrals to gravity was Charles Meissner. I mean, John Wheeler's student and co-author of that famous book, Meissner, Son and Wheeler. And you can of course just generalize this to a formal expression set of G, which is integral dg u nu of x e to the I s of g mu nu of x. Now you sum over all now metrics. So you see this is already a big step from summing over all fields in Minkowski space to summing over all space-time in a sense. Of course, you add then here other fields. I mean, of course, if you have matter, then you should add this. This is just for vacuum gravity. So what it means is, so I should write plus matter fields. So you sum over all metrics on a four-dimensional manifold M, of course quotiented by diffeomorphism. That's what you would like to do. In principle, you should also maybe sum over all topologies. Why not? Yeah, not just say spheres, but tori or. But this is it's easily said, but it's in practice not possible, because in 4 dimensions this cannot be classified as manifolds. You cannot really write down something precise. You can do it in 2 dimensions. This is why string theory works. But in 4 dimension, I mean, if you want to implement it here, it's just not possible. You would have to find some other arguments why only some topologies are relevant, or why the sum has not to be formulated. Okay, then what about the Euclidean formalism? So, okay, there are differences now because this affects really the space-time. First, not every Euclidean metric, even if you made this, if you have a metric in the Euclidean time tau, has a Lorentzian section. Yeah, for Minkowski space, that's somehow trivial. But for example, if you have the Kerr metric, which has terms d phi dt, if you go to tau, then you have explicit i's in there. And so that's a general problem. Not every Euclidean metric has a Lorentzian section. No. And even more severe, the Euclidean action is not bounded from below. So Euclidean action. So if you somehow had this big rotation, you would write this Euclidean version of the Einstein-Hilbert action. Then you sum over m d for x, the square root of g, so that's the Euclidean metric. And then you have r minus 2 lambda, and plus a surface term, which contains, I mean, the second fundamental form, and which we will not discuss here. And if we consider now a class of metrics by having g mu nu going to g mu nu tilde is just conformally related to g mu nu. Then if you sum over all metrics, of course, part of it is a sum over all omega. And so integral d omega is part of integral d g mu nu. And if you only consider that part, then so we have SE evaluated for this conformally transformed metric. Then what you get is, and okay, this follows from calculations, minus 16 pi g to the minus 1, and then you have the integral over m d for x, the square root of g, and you get omega factors here, and also omega derivatives. So the covariant, which is called here the ordinary derivative, so respect to x mu, g mu nu minus 2 lambda omega to the 4 plus surface term. Now you see a problem. I mean, of course, these expressions, they appear in the path integral, and you see here this. I mean, the omega is general, so you also have here omegas with rapidly varying derivatives, and also they can be made arbitrarily negative. So this can be made arbitrarily negative by choosing a strongly varying omega, and then of course in the path integral, if you have, say, here an e to the, so integral the omega e to the minus se of g mu nu, okay, this also has the other terms, then, I mean, arbitrarily negative, then this diverges. And so you're somehow puzzled. Yeah? You say, okay, the old methods from standard quantum field theory do not work. So this is called the conformal factor problem. And of course, one may think about curing this by dividing some parts out and so on. And some people have made suggestions for doing that. For example, Dasgupta and Lal in 2001 have written a paper to the effect that that this conformal divergence cancels against a divergence from the measure with opposite sign. Yeah. Okay, this is very technical, but it seems to indicate that there's a possibility, although it's not finally settled. Now, still, in spite of these problems, the path integral is employed in quantum gravity. So use for semi-classical considerations, because there you don't have to deal with the full path integral. For example, in quantum cosmology, to which we come later, there's a so-called no boundary proposal by Hartle and Hawking. Okay, which is formulated at a general level, but to evaluate it, you have to go to semi-classical evaluation. Also numerical evaluation, as for example you do in Recce calculus, or in more modern terms in dynamical triangulation, yeah, where actually a Lorentzian formalism is used. So unfortunately, in this very short lecture, I will not have time to elaborate on it. So I suggest you can read the sections in my book and the references that lead beyond that. And of course, the development of Feynman rules. So we have already encountered some problems connected with the path integral formalism of quantum gravity, which is of course present also in other formalisms in different ways. But there's also, concerning perturbation theory, also one other major problem that is often understood as a maybe no-go thing of quantum gravity, which is not a modern expectation. This is non-renormalizability. It's a problem with the perturbation theory, but it could, in principle, or go away in the full non-perturbative regime. So, but I have to explain what this is. So, this is perturbative non-renormalizability. So usually in particle physics, what you have some ingoing particles, and then you have a complicated interaction region, like in CERN when all these particles hit, and then you have some outgoing particles. And so this you choose somehow. Say in lecture, this is what you observe, and you have to then conclude something about this here. So this is the ingoing particles and outgoing particles, and this is some interaction region, usually not known in detail. Yeah, and these are asymptotically free situations where the interaction is small. Now, the main problem here, if you do this for quantum gravity and calculating processes, is the so-called non-renormalizability. So what is that? So we call a theory renormalizable if all these divergences in quantum field theory can be removed, and removed by a redefinition of a finite number of parameters. We know that in quantum field theory there are always divergences coming from the sum over arbitrarily high momenta or arbitrarily small distances, as long as you invoke a continuous space-time. No? So let me have here this definition. So a theory is called renormalizable. Yeah, if the divergences in quantum field theory, so I don't write this here out, can be removed by a redefinition, and this is what we call renormalization of a finite number of parameters, of a finite number of parameters of the theory. That's so. For example, in quantum electrodynamics, which is the paradigm for quantum field theory, and it's renormalizable. These are masses and charges. I mean, the charge and the mass of the electron, and so you have divergences, and you can swallow them by these two parameters. Of course, then you cannot calculate them. They are there in the formalism, and just for this purpose, in a sense, and have to be measured. Then, so you only have the measured values, which is a sum of a naked value, which is say minus infinity, and a divergence plus infinity, such that a finite value remains, and this must be measured. That is, non-renormalizable theories need infinitely many parameters to be measured. Of course, you should not start to do that. This is very much, and it does not mean to make sense. So earlier on, I mean, this was then interpreted as that is in the sense that the theories do not make sense, but the modern point of view is that they can still make sense as so-called effective theories. That is, they have a limited range of validity at not at arbitrarily high energies, but up to some value. No. So non-renormalizable theories have need infinitely many parameters to be measured. Okay, then does not make sense, but question mark can make sense. So theory can make sense as an effective theory. I mean, valid, not universally valid at all energies, but only up to some limiting value of energy. Actually, quantum electrodynamics, which is renormalizable. Also, we do not think that it's an exact theory for all energies, because there's also the so-called Landau poles that you discuss here. Okay, this is at very, very high energy, but it also presents the problems. So it seems that most of our theories so far are effective theories, whether they are renormalizable or not non-renormalizable. So we should not be worried too much about the non-renormalizability of quantum gravity, as I will show you, as long as we can get definite predictions from the formalism. Now, in quantum field theory, of course, there's a long discussion, and for example, you may consult your favorite textbooks on quantum field theory. One is certainly Weinberg's volume 1 of quantum field theory, and there you can consult section 12.3, which I follow here briefly summarizing it. So there it's also discussed that an important criterion for the non-renormalizability is, or the renormalizability is, so-called mass dimension of the interaction. Now, if you set h bar to 1 and c to 1, then you only have a mass scale. I mean, you can translate lengths and times into masses. So every physical quantity has a mass dimension. Could be mass dimension 0, so it's dimensionless. Could be 1 over mass or mass squared. And actually, this mass dimension is relevant because it's negative for a non-renormalizable theory. Of course, this is not really a rigorous statement, but it's an indication that is usually correct. So in quantum field theory, mass dimension of an interaction. So if you have h bar equals 1 and c is negative for a non-renormalizable theory. Okay, and so you must inspect the dimension of the coupling. Dimension, I call it delta of a coupling. Yeah, how to? This is not too difficult to calculate if you know how the Lagrangian is, and I give you the expression that you find in Weinberg's book, and you can check that this is correct. So delta is here defined as 4 minus d minus the sum over all f, and f is f plus 1. So this is the number of derivatives. Because I mean, for each derivative you have a negative space, also a positive mass dimension. And this is the number of fields. Of type F, with SF is 0 for scalars, 1/2 for fermions, 1 for massive vector bosons, and 0 for photon and graviton. And so, for example, if you look again at our favorite example, quantum electrodynamics, then there the interaction that you have there, that you use in your QFT class, is minus I, then the electric charge, psi bar, so you have the fermions, A mu, the Dirac matrix is psi. Now, so that's the, I mean, those of you who have studied QED know what I mean. This is the QET interaction. Let's just check now here what this gives. So for this, then the delta is 4. Okay, this is always 4. There are no derivatives here. So this is minus 0. And then you have to have here, I mean, you have fermions, right? This is 1/2 here. Well, you have here minus then 3/2, one, which is from the psi, and again minus 3/2 from the independent psi dagger. And then you have the a mu, which is just, okay, it's a photon, so it's 0, the s, and you only have here the 1, and you have here 1, so this is -1, and so this gives 0. So which means you have a vanishing mass dimension stating that the coupling is dimensionless, and in the natural units the electric charge, which is the coupling, is dimensionless. It's the fine structure constant, if you like, E squared. Yeah? So coupling is dimensionless. So recall we have E squared over h bar c is approximately this famous number. If you had another term, there's so-called Pauli term in quantum electrodynamics, you get a negative mass dimension, and this is why this is non-renormalizable. Now, what about quantum gravity? Of course, there are two famous people have to be mentioned. I mean, Gerard 't Hooft and Martin Feldman. Well, in 1972, they have shown that the so-called Young-Mills theories, which are non-abelian gauge theories, are renormalizable. Are renormalizable. And so this gave a big boost then to the study of the Standard Model, because the Standard Model, a famous important ingredient is this gauge series, and if this is renormalizable, it means it seems that by measuring finitely many parameters you can have, I mean, as arbitrary many predictions you want, and then it's a viable theory. Actually, this is what earned them the Nobel Prize in 1999. So this is very theoretical, but because it's so important for also experiments, this is what convinced the Nobel Committee. So the Standard Model of particle physics, Standard Model of particle physics is renormalizable. But then they also asked the question, what about the gravity? And because that's not part of a standard model, so they then used the ansatz we had developed last time, with the metric being sum of a background and a perturbation. Okay, last time we used just the Minkowski background, but of course we can use any background, Schwarzschild or whatever you like, Friedman, Robertson, Walker, and then the perturbation, which is then written here in this form. I mean, we just wrote here f mu nu, and as I said, it's small here. You extract this square root of the gravitational constant. This is just convention here. Why? Because then f mu nu has a mass dimension like other fields, quantum fields that you usually have, like phi's and so on. So it has just dimension of a mass. But that's in principle a convention, and you can do also without that. So then has dimension of a mass. I mean physical dimension, like many other fields. And so that's just the background, which is taken to be a solution to Einstein equations. So that's not quantized. In this linear approximation, you assume there's a background, and then you have quantum fields. Now, for example, if you take this to be the Minkowski space-time metric eta, then you get from the Einstein-Hilbert action the action which we call the Fierz-Pauli action last time, which is just a quadratic action in F. So if you take g mu nu bar is the eta mu nu, then I mean get from SEH, I mean the Fierz-Pauli action, when integral over Fierz-Pauli Lagrangian. Okay, as long as you have the first order, well, the order in the action f squared, but of course if you go to higher orders and if you want to quantize exactly, that's what we want. We have then plus terms of higher order of the form, and this is a symbolic notation. Okay, so we have then square root of 32 pi g times f df. What I mean is here terms of third order where you sum here over indices. Yeah, and can be very complicated, but you have here two derivatives and plus higher orders plus then, okay, generally you have here, it turns out, times f to the r's power, and you have here df and so on. So you always have only two derivatives because the Ricci scalar has only two derivatives that you expand. No? So always, I mean at all orders, always. So this has higher orders here, but this only two derivatives. Always two derivatives. No, because R has two derivatives. Okay, you have infinitely many terms, no, because you expand from the following, from the expansion of, I mean, in the Einstein-Hilbert action, you have the square root of minus g r mu nu g mu nu. No? So this is the determinant and this is the inverse of the metric, and if you expand this in this form here, then it's clear you get arbitrarily many terms. There's no end, I mean finite end. I should here say perhaps here that De Witt in 1967 already has imposed the principle that the formalism should demand covariance with respect to the background, so that no particular background is preferred. And this is called the background field method. No? So background field method, going back to Bryce De Witt in 1967, means that you have covariance with respect to two redefinitions of the background, so that no particular background is preferred. You can do this also in other quantum field theories. Okay, so let us inspect this term and let us see about the mass dimension. So let us apply then this formula here, and so here if we have this here, so we have here delta. Well, it's clear that here, I mean, you have here d equals 2 because you have two derivatives. You have three terms, f, so n equals 3, and you have here the graviton, which gives here in this formula this number 0. So if you apply this formula, you have then 4 minus 2 derivatives minus 3 fields times 1. So this gives, I mean, that the delta is 4 minus d minus m times s plus 1. So this is 4 minus 2 minus 3, and you have 0 plus 1, which is minus 1. And so you have a negative mass dimension. Of course, this is because here the coupling is square root of g. square root of Newton's constant, and if you set h bar and c equals to 1, then of course this is 1 over the Planck mass. So it has a negative mass dimension. And so we expect non-renormalizability. Actually, if you then write down the path integral and expand in terms of quantum loops, then it will be an expansion of h bar, but also square root of g. Now, the expansion of the path integral in terms of loops is an expansion in terms of, h bar to the power of that loop, and g actually, well, it's one power less. No? So L is the number of loops. Okay, so it's non-renormalizable. This is actually what also turns out if you do the explicit calculations. Some remarks, for so-called R squared theory. So if you have instead of the Einstein-Hilbert action, a generalized theory where you have R squared, then you can get renormalizability. This is what Steller in 1977 showed, but at the price of giving up unitarity, which is means conservation of probability in quantum gravity. More recently, there are so-called Hoshava-Lifshitz theories from 2009. There you have renormalizability and unitarity, but at the price of violating Lorentz invariance, and also thus the equivalence principle at high energies. So that is, you can move this problem somehow around by going to other theories, but it's very difficult to get one where none of these problems is there. And this has to do with the fact that we are dealing with gravity and with a dynamic background. Now, to work explicitly with path integrals, the standard way in the last decades is a so-called Fadeev-Popov procedure. For explicit work with path integrals, you have the so-called Fadeev-Popov procedure. Going back to a 1967 paper by Fadeev and Popov, although some elements were already discussed by de Wit a couple of years earlier in 1963, 1964. And that's what you usually learn when you learn modern quantum field theory, for example, going to such books as Weinberg's book, already cited from 1995. And of course, there is no place here and no time, unfortunately, to really discuss the Fadeev-Popov procedure in detail. The point is, you can read it in the book and elsewhere, but the point is, this is a procedure to make the path integral, well defined in these limits and handleable. So you make this expansion here. You can also call it the application of the background field method, and you have the path integral in the form integral df mu nu. You sum over the quantum field, and you have e to the is, and you have your f mu nu and g mu nu bar, and which you can call integral df e to the is of f d bar, suppressing the indices. Formally, if you don't do anything, this is infinite, because this here is invariant under f mu nu going to f mu nu minus d nu epsilon mu minus d mu epsilon nu, which we may call f mu nu epsilon. And so if you sum over all f, you also sum over all this coordinate related, and so you have an integral d over d epsilon here without anything depending on epsilon. No? and this gives an infinite expression. So the Faddeev-Popov procedure is then a procedure to make this finite by involving 5 steps. Okay, made finite and tractable in 5 steps. That I will just say in Word. You have to first impose a gauge condition. I mean, so that, or coordinate condition, so that this is prevented. That's certainly the first step. So you only integrate over a submanifold of all fields. Then you define a so-called, you have to make a transformation in the fields, and this gives you kind of Jacobi determinant in the transformation, which is here called the Faddeev-Popov determinant, and which has to do with the imposition of this gauge condition. Finally, you have this determinant, which is very ugly to be in the path integral. It's written by some identities as an e to the I additional action. And because this is just a mathematical procedure, this additional term which has additional fields, they are called ghost fields. So you will have then a new action with gauge fixing and Faddeev-Popov ghosts plus the original action, and from this you develop Feynman rules. And then everything should be correct, as is done for the Young-Mills series. As you can imagine, this is really tedious work, and so you need really be a specialist to do that. You cannot just do an exercise now to do that. I mean, you have to work a couple of months at least. But of course, that's has been started in the 1960s, and much work was already done in the 1970s. And clever people have done that. For example, de Hooft and Feldman in 1974 have done calculations. For example, they have done also extracted the exact divergent term for that. So the divergent part at 1 loops that you have to handle for absorbing infinities, and this was this famous expression h bar over 8 pi squared 4 minus d, so r squared bar squared plus this term, with epsilon is 4 minus d, and d is the number of space-time dimensions. So you see there's a divergence in 4 space-time dimensions, and to handle that divergence you go to other dimensions where you explicitly isolate that, and you can then swallow up this in other terms. Actually, this vanishes for vacuum gravity. So if vacuum gravity has r mu nu bar equals 0 from the Einstein equations, so that's why some people say, okay, well, we expect non-renormalizability, but in fact, miraculously, this vanishes. But you already, when you add matter, this is non-vanishing, and it was then shown by some very brave people who could do, complicated calculations in the 80s that had 2 loops, 2 quantum field theory loops. You have here terms that are even for vacuum are non-vanishing. So you see perturbative quantum gravity is non-renormalizable, but we can treat it as an effective field theory and even calculate effects. And this is the last thing I write down. So one can calculate effects at 1 loop. one quantum field theory loop. And so, for example, the quantum gravity correction to the Newtonian potential. No, so which was achieved by Bjerrum, Bohr et al. In 2003. Bjerrum, Bohr in Copenhagen, so relative to the famous Niels. And what was found was potential V. So if you have two masses, M1 and M2, so they attract each other by this Newtonian potential. And if you do now quantum field theoretic calculations along these lines with the Faddeev-Popov procedure, the ghost, and so on, it has taken years actually to do that. There were first some other papers who somehow missed some diagrams, and only then here there was an agreement in the community that calculation is correct. So this is far from trivial, even if this procedure is clear. To do the calculation, I mean, is really hard work. And but the result here is actually then quite short. So you get two correction terms, so 3g m1 plus m2 over rc squared. So I introduced here all the units, and you get here the second term, which is plus 41 over 10 pi Planck length over r squared. So you find here at this order really two corrections to the Newtonian potential, and so there is no ambiguity if you do it correctly, of course, but that's about your abilities. No ambiguity in this. You see, the first term actually has no h bar in it. So actually this gives a correction term from classical general relativity. I mean, this is just Newton, and this here gives a correction from classical general relativity, actually to calculate, say, perihelion motion of Mercury. If you do it in that formalism, I mean, you get such a term. No? So you get, very interestingly, in this path integral, a GR effect back. And here this red term is really quantum gravity effect, so Planck length over r squared, so 1 over r squared contribution, which is then 1 over r cubed all in all. If you say, okay, great, so let's measure this, yeah, good luck, but you see, if you estimate here, you see, I mean, this is the Planck length, 10 to the minus 33 centimeter. So if you go to make a Cavendish balance experiment, you would have to approach the masses towards the Planck scale. And I mean, we are far from able to do this. I mean, I do not know what's the current limit, maybe micrometers or something like that, but certainly not 10 to the minus 33 meters. But anyway, it was not expected that one has here a measurable term, but it shows that quantum gravity is not something just pure in the air and hours of formalism, but that in principle at the end you should get some numbers. And if the numbers are small, then this has to do with the scale. I mean, if the Planck scale were bigger, you could measure it. Okay, so far for today. Of course, there would be much more to say on the covariant formalism, on the higher loops. Also, there are currently interesting supersymmetric generalizations which seem to higher orders give cancellation of divergences. So maybe that's the correct way to do it. I should also mention the asymptotic safety approach, which I also discuss in the book, and which you find in literature. Then the already mentioned dynamical triangulations. So there's a lot of activity going on in very different ways, but more or less starting from this here. Also, one can at the one loop in this formalism write down the so-called effective action, discuss it, and for example discuss the semi-classical Einstein equations in some limit with the expectation value of the T mu on the right hand side that we had in chapter 1, and it follows here as an approximation. Okay, but this concludes chapter 2, and so the next chapter will be then, or at least an intermediate chapter, preparing the canonical formalism. the Hamiltonian formalism, which views the same issue, the same problems, but from a totally different angle, and also has its advantages and problems. Okay, so thank you for listening, and see you next time.